we have defined the propositional equivalence and the De Morgan's law we have read. Now, we see some more laws that are very useful to derive or to check the equivalence between two compound propositions. So, first we see one theorem. And so, we continue the propositional equivalence. Okay. Continue. So, first we read one theorem. It gives a relation between the conditional proposition and the contrapositive of the conditional proposition. So, the conditional proposition say P implies Q and its contrapositive that is negation Q implies negation P are equivalent. We prove by truth table. So, if we draw truth table, P implies Q and then negation P, or first we give the negation Q, because that will help us to write the truth values. Then negation Q implies negation P. All possible assignments of P and Q. So, we evaluate. If we remember, we read in last class that what is P implies Q? If P Q both are true, so this is true, but true implies false, we have taken these as a false result. Remaining cases they are true. Now, negation Q, so this negation Q becomes F, T, F and T. Negation P, there F, F, T, T. So, what is negation Q implies negation F? F implies F, true. T implies F, again this is F, F T, this is true, T T, this is true. So, we see that P implies Q takes the truth values T F T F and negation Q implies negation P is T F T F. That means, both are taking the same truth values for the same set of P and Q values. So, they are equivalent. So, they are equivalent. So, it is proved that they are equivalent. We take one example. if you fix my computer, then I will pay you rupees 500. Then I will pay you rupees 500. So, this is the compound proposition, because this is a statement. So, what are the primitive statements here? Primitive statements say I take P is you fix my computer. Okay. P is you fix my computer, and Q is I will pay you rupees 500. So, this statement, the example statement tells that P implies Q. So, if it is my compound statement P, then it is telling that P implies Q. Now, I will not pay you if I write that I will not pay you rupees 500 if you do not fix my computer, if you do not fix my computer. So, I will not pay you. This tell I will not pay you rupees 500. This tells that it is negation Q, not. So, it is negation Q implies if you do not fix my computer. Again if it is if you do not fix my computer, do not, that means again it is negation P. So, if I tell this compound proposition is negation Q implies negation P, then these two statements are same, that means P is same. So, P is equivalent to Q, that means if you fix my computer, then I will pay you rupees 500, or I will not pay you rupees 500 if you do not fix my computer, that are same, that are logically equivalent. Now, we see some other rules of, or we call that laws of logic. Okay. Okay. So, only one law we have read, that is De Morgan's law. Now, we will see that there are many other similar type of laws that we can apply on the compound propositions and the primitive statements that makes these compound propositions. So, first we tabulate that this type of laws. Or okay, first we see that the law is the very primitive laws that we can tell that the it is double negation. Since we know the De Morgan's law by how to negate a one compound statement. So, we read that negation of negation P is equivalent to P itself. We call this is double negation. Now, already we have seen that single negation, which is nothing but De Morgan's law. I can write negation Now, we see that these propositions that they follow the our basic algebraic laws, the law of algebra like commutative, associative, distributive laws. So, that is why sometimes we call these are the laws of propositions. Okay. So, first we see that if I consider the connectives at the conjunction, that means P and Q, this is equivalent to Q and P. Then P or Q, this is equivalent to Q or P. This we called our commutative laws. Then associative, so this is our associative laws. And here our PQR are primitive statements. Now, we see we read some more rule. So, we read the associative to commutative and associative, we see the rule distributive. We have PQR So, we take P and Q or R, which is equivalent to P and Q or P and R. Similarly, if we replace and by or and vice versa, or then this similarly I get P or Q and P or R. So, these are my distributive laws. Now, there are some more basic laws that we tell. One is, if I take P and in conjunction with P itself, that means P and P, we take P and P, then it is P only. Similarly, if I take P or P, it is P. These two are called the rule, the idempotent. This is of idempotent laws. Now, if I take the conjunction and disjunction with the true and false only, that means, if I take the P or F or P and T, then also P or F, because we know that whatever the P has the value true or false, it will take that value. So, it is P only. Similarly, P and T, this is again P. So, this is called the identity. These two are our rule of identity. Now, we have some other rule we call that inverse. So, if I take again the conjunction of negation P, we have already seen that this will be false. If I take P on negation P, this is always true. So, these two are inverse rule of. Okay. Now, I have, if I take the P or T, we will get always T, we give P and false, we get always false. So, it is our domination laws, it will dominate, the true and false always dominate. So, this is our rule of domination. Now, another important is the absorption. This is very much required when we try to simplify the compound proposition. So, absorption is that if I do the P or P and Q, then it is P only. and P in conjunction with P or Q, then also it is P. Why? See, here it is P or. So, whatever be the value of this P and Q, it will take the truth value of P. Similarly, here P and P or Q. So, P or Q is P, just the logic we gave, and then P and P is P. So, this is the rule of absorption. Rule of absorption. Okay. Now, we have seen the negation where the proposition becomes when we take negation in De Morgan's rule, the proposition becomes the negation of that particular proposition, and the conjunction disjunctions, they are actually exchanged. Now, one is called the dual, and if that we dual of proposition P. Normally, we denote this thing as PD. So, here if how we define the dual, if the proposition P contains only the logical connectives, and or and no other connectives are there, then the dual of P is obtained by replacing, or I can tell by replacing and by or and or by and. Then it is dual. Please note that here there is no negation concerned, because my proposition contains only the connectives and or. Now, we see that some of the, now we have read the laws, and now applying these laws, how we can check whether the two compositions or compound state propositions are equivalent or not. So, first we see one conditional proposition, the equivalence of the conditional propositions. The equivalence of conditional proposition. The conditional proposition, we know that P implies Q, and if P implies Q, that it is equivalent to negation P or Q. This is one. I can write that negation of Q is equivalent to P and negation Q. This is nothing but if we apply the De Morgan's law on both the side. So, how we can prove that thing? If we try to prove, always we will prove by making the truth table. So, we draw the truth table. We take all possible assignments as usual. Then P implies Q, it is true, only this is false, true, true. Now, negation P is false, false, true, true. Now, negation P or Q. So, this is my negation P and or Q. So, T or F, this is T, F or F, this is only F, T or T, T, F T, this is T. So, if we see P implies Q and negation P or Q, and they are taking the same truth values. So, it is proved. And in the second case, if we just apply for 2, if we apply De Morgan, apply De Morgan's laws, then the left hand side, that it is P implies, because already we have proved that P implies Q is equivalent to negation P or Q. Now, we apply De Morgan, this is negation of P or Q. So, this is equivalent to negation of negation P Q, this is negation of negation P and negation Q. Negation of negation P is P only, double negation rule, and this is P implies P and negation Q, which is the second one. So, it is also proved. So, this is equivalence of conditional proposition, that is the we consider implication. We consider the implication. Now, we see that if we consider our equivalence of biconditional proposition. So, we know our biconditional proposition is, if P and Q two proposition, it is if and only if Q if and only if P. Now, we give that biconditional proposition is equivalent to P implies Q and Q implies P. then the proof will be we take all possible assignments. Then it is biconditional if P then and if Q if and only if P, or if P only and if only if Q. So, whenever both are taking the same assignments, then only it is true. So, T T true, F F true, and the remaining cases it is F. We know P implies Q is T F T T, Q implies P. So, it is T T F T, and this is and. So, T T T F T F T F F, and this is T. So, again you see that this is biconditional. So, our LHS that it is T F F T, and the RHS this is T F F T, that means these are equivalent. So, it is proved. So, they are proved. Now, if we see that what we have seen that to equivalence of two conditional proposition, one is P implies Q is equivalent to negation P or Q, and is equivalent to P implies Q and Q implies P. Now, another is that substitution rule. That means, if substitution is see if the for we take that P, the P and Q, the small p, it is equivalent to R conjunction S, okay, R conjunction S, and Q is say U or negation T. Then in one, what we can do that by substitution rule, that P implies Q, this can be equivalent to the, if I P, I can instead of P I can write S, R and S, then or instead of Q I can write that U or negation T. Here PQ as well as RSUT, here RSUT, T are the propositions. Are the propositions. Okay. So, I can write actually if I can take that P is same as that of R and S, then on this substitution we can apply. So, in this way we can similarly we can apply the equivalence of the biconditional proposition also, and we can evaluate the compound propositions for it and we can simplify it, and then we can check whether two propositions are equivalent or not. Now, we give an example that how the laws of logic can be applied to simplify the compound proposition. Take one example. Let us simplify the compound proposition P, which is P or Q, and negation P and Q. Here P Q are primitive statements. So, we start from the given compound proposition. So, P, which is P or Q and negation P and Q, and we apply the laws of logic. So, this is equivalent to P or Q, and we apply first De Morgan's law, because it is we have to negate this expression. So, it will be negation of P, this AND becomes OR and this becomes negation Q. Then immediately we should write that what law we have applied here. This is De Morgan's law. Now, this will be double negation. So, this becomes only P or negation Q. So, we write this is use of double negation. Now, see, this is P or Q and P or negation Q. So, this is the distributive law. So, we can use the distributive law, or we can apply the distributive law of or the disjunction over conjunction. That means, I can write this thing P or Q and negation Q. So, I write this is the distributive law. So, Q or negation Q, Q or negation Q is Q and negation Q is F, always false. So, this is my inverse law. and this becomes P or F. So, this becomes only P, which is identity, So, my compound proposition that capital P becomes only the primitive statements P. This is simplified to small p. P is simplified to small p. So, it is simplified. So, this example tells that how the laws of logic that we have read, the different laws that can be applied to simplify the compound propositions. So, we have now we can conclude this lecture with this example.